Alright, silly people, here's the situation. We have this wave function for a particle that we are just kind of going to talk about as representing a free particle. No boundary conditions, no potential, just moving through space. Um, so, first thing we can do is normalize it by integrating the square modulus of the wave function over all space and setting the result equal to 1. Because it's a absolute value integral, I'm going to split it up into a couple different regions, one of which being where x is negative, and so we can change the integrand to actually positive e to the positive 2ax dx. And then from 0 to positive infinity, so where x is a positive number, and it's just going to be that. And set that equal to 1. So these integrals are not too terribly hard, because this is just going to be e to the 2ax over 2a from minus infinity to 0, and then this guy is going to be minus e to the minus 2ax over 2a from infinity to 0. Right. And so e to the 0 is 1, so we get 1 over 2a, and everybody knows e to the minus infinity is basically 0, so don't even worry about that. Then we get another e to the minus infinity, so also 0, and then we get plus e to the 0 over 2a, so just another 1 over 2a. So from that, it's looking like a is just root a. So we can represent the time-independent wave function like that for future reference. Then the problem asks us to calculate this phi of k thing, which is defined as being 1 over root 2 pi from minus infinity to infinity, the time-independent wave function e to the ikx dx, which effectively is a Fourier transform of it. So it kind of just represents the wave function in momentum space rather than in position space. So for us, we've got a root a here. It's going to be the integral from minus infinity to infinity of just e to the minus a absolute value of x minus ikx. And then just kind of do that integral. So that absolute value is going to make us have to split it up again. A couple different integrals, one of which will be in the negative space, so e to the plus ax minus ikx dx, and then another integral in the positive space, e to the minus ax minus ikx dx. Right. So those integrals again aren't too terrible. And I'm going to actually open up parentheses now instead of a bracket. We've got e to the ax minus ikx over a minus ik from minus infinity to 0, and then plus minus e to the minus ax minus ikx all over just a plus ik, which we evaluate from 0 to infinity. We can just plug in those endpoints now. We just have root a over 2 pi, and then this is going to be 1 over a minus ik, and this is going to be 1 over a plus ik, which we can simplify by a bit. Get rid of those pesky imaginary symbol, so we'll have a plus ik plus a minus ik over just a squared plus k squared, and then those will simplify. You get a 2a up top, that fraction, and then the denominator is just that stuff there. So that's cool. Then the problem asks us to construct the time-dependent wave function, which for the free particle is constructed from 1 over root 2 pi times the integral over all space. The Fourier transform of the wave function times e to the ikx minus I omega t dk. So this is kind of an inverse Fourier transform. So we have 1 over root 2 pi, and then we have a root a over 2 pi from the phi of k thing. And then we also have a factor of 2a. But in the integral, we have from minus infinity to infinity e to the ikx minus I omega t all over a squared plus k squared dk. And then the problem just asks us to leave it in the form of an integral. So all I'm really going to do is simplify this a bit, and actually that 2 will cancel out, so it'll just be root a over pi times the crazy integral. And there's also another power of a up here. Yeah. A squared plus k squared dk. But then the problem asks us to look at the limiting cases, those being a goes to infinity and a goes to 0. So let's look at a Desmos plot that I've set up, actually. All right, so right here on the screen, I've got the wave function psi of x in red. You can see that it's an absolute value function because it has a sharp peak at x equals 0. And in the blue, I have phi of k, which is kind of, again, the wave function in position in space, in momentum in space, I mean. So in the case where we let a be really, really large, I'm just going to put a bunch of zeros on the end of this. So 0, we already see that the position space wave function sort of sharpens around x equals 0, and then the position space one broadens out quite a bit, and you can keep going up and up and up and up. And now the position is really, really well defined as being right here. But momentum is spread out over the entire space. So you know really well where the particle is, but you have no idea how fast it's going in the limit where a is really, really big. By the same token, we can look at the case where a is really, really small. So right then I just divided it by 10. And now the momentum representation is sharper, but the position representation broadens by a lot. And we can keep just going smaller and smaller and smaller, where now a is basically going to 0, and we see that now we know really well how fast the particle is going. We know what the momentum is, but we have no idea where it is. And so that just kind of goes to show when you mess with the constants by which your wave function is defined, you'll either know a lot or a little about what it's supposed to be representing. All right.